which corresponds to about 3 microns, the current that we can get from that photon flux, if we could capture those photons, is huge. It's 1.7 gigaamps per square meter. So there's a lot there. It's worth looking at if we can get it. This zero-point energy was since it's the universal ground state, that means that we can't induce a flow by having a change. The second is that these fluctuations are extremely short-lived. So let's take a look at these in turn. Can we modify our ground state? And most of you know that yes, in fact, we can. It would be a little bit like having an ocean, a sea level, and we could then all of a sudden dig out, like Moses, a little region of the sea that was at a lower level. So if we could do that with the vacuum energy and dig out a region which is at a lower level, then we could induce a flow. And we can do that with a Casimir catheter. Most of you know this was developed by Casimir in 1948 and then finally proven to work at the end of the 20th century. The basic idea is that we've got two closely spaced mirrors. In between these mirrors, we have the boundary conditions at the mirrors saying that the electric field goes to 0, and so we have a restricted number of modes. It's an integer number of half wavelengths that can exist within this region, whereas outside we have the full spectrum. Therefore, there's more radiant energy outside than inside. There's a net force, and these two plates should collapse. And in fact, they do. What I'd like to take from this for today's discussion is that this is sort of it blocks all the low frequency, long wavelength modes in the zero-point energy spectrum. All right. So we talked about modifying the ground state. What about these short-lived fluctuations? There is a quantum inequality developed by Larry Ford a number of years ago, and he says that an energy delta E may be borrowed from the quantum vacuum for a time delta T. And so it's an uncertainty-like relation. I'm here putting it into the uncertainty formalism, although the number here may not actually be h bar over 2, Planck's constant, over 4 pi, but instead maybe a different number. But it's something like that. And so the basic idea is that you can have radiation that can have a substantial amount of energy, delta E, if you look at it for just a short enough time. So these things pop in and out of existence, these photons and pairs of virtual particles pop in and out of existence. So how much energy and how much time? If you say we want 2 eV light, 2 electron volt light, which is red, then that says that our time uncertainty, or perhaps the time that it can be borrowed for, is less than a femtosecond, about a tenth of a femtosecond. So extremely short. They're just very, very ephemeral. All right, so this is borrowing energy from the vacuum. What would happen were sneaky, and we borrowed the energy and captured it quickly. What would happen then? Can you do that? Traditional physics has not addressed that. All right, so now we've talked about zero-point energy. Let's now talk about our devices and then get into the results. The basic device consists of a metal insulator metal structure. So this is a thin metal that's semi-transparent. This is a very thin insulator which allows electrons to tunnel or hop over this barrier, and then the base metal is a little bit thicker. So if we imagine this thing just sitting in equilibrium in steady state, we've got zero-point energy modes in the base metal. These are dominantly for visible light and energies. These are dominantly in the form of plasmons. And so these plasmons will have a distribution. There'll be fluctuations that can create a sufficiently hot electron to go across the barrier to the top metal. Similarly, in the top metal, there are going to be these plasmons powered by zero-point energy that will create electrons that can go in the opposite direction. But this top metal is a little bit thinner, so there were fewer of those electrons. On the other hand, there also are the external vacuum energy modes. And so these external vacuum energy modes can energize an electron by the photoelectric effect. That electron, that hot electron, might be able to traverse this thin metal, both across the insulator and get to the bottom metal. And so in this way, if we're sitting in equilibrium, these two arrows are balanced. There's no net flow. I haven't gone into the details of virtual particles or anything yet. There's more subtlety here. Okay, now let's put a Casimir cavity on top. We just found out that the Casimir cavity blocks the low frequency modes. And so that means that we're now going to have fewer electromagnetic modes from the zero-point field impinging on the top surface, and that diminishes the size of this arrow. So we've now, notionally at least, broken this balance. And so the detail balance between down and up has changed. We now have a net electron flow from the bottom to the top. I don't claim this is a rigorous model in any sense. It's simply a notional idea of what's happening. So this is the basic structure of our device. The actual implementation is shown here. We start with a silicon, with a glass silicon dioxide coated silicon substrate, put a base metal of nickel on it, then a very thin double insulator of nickel oxide and aluminum oxide, and then a thin layer of palladium on top. To form the cavity on top, the Casimir cavity, it would be nice if we could use vacuum deposition. Vacuum deposition doesn't mean depositing a vacuum, unfortunately. So it means we have to put some sort of a thin, transparent medium in. We're using either an organic or glass or as our transparent medium, and then we put the mirror on top. The measurement circuit goes between these two metal electrodes in the MIM device. This is a scanning electron micrograph of one of our devices. As you can see, they're quite small. The dimensions are about 1/10 of a micron by 2/10 of a micron. And so we built these devices. I won't go through the history of it. I've talked about that in our previous talk. Instead, I'll just jump to a result. So we did find a significant change in the current voltage curve. So this is current as a function of voltage. For a device with a fat Casimir cavity, we have the red line, and that's an 1100 nanometer cavity. When we make a narrow Casimir cavity, that's the blue line, the resistance decreases substantially. That is, we get more current per unit voltage. And so we see what I'm calling a Casimir doping effect, that the more modes that we that is in the thin cavity, the more we reduce the resistance of the device. And we published this result in a Physical Review research article at the beginning of last year. And more recently, Larry Ford has applied some of his theory to looking at this and says, yes, it does look plausible that the Casimir cavity does in fact induce some injection into the metal insulator metal device, which would then give us the reduction in resistance. But this is a fairly large voltage scale for these tiny devices. We're plus or minus 0.3 volts. What happens if we look right in here in this region for the very low voltage and very low current? Well, if we do that, we find the strange and intriguing result that the curve does not pass through the origin. If it doesn't pass through the origin, that means it's either using power or producing power. In our case, it's producing power. Solar cells normally operate in the first quadrant. Our devices operate in the third quadrant, which is also a power production quadrant. So we actually are producing power in these devices. And the power is substantial. For some of our better devices, we get about 70 watts per square meter. Now, I have to add the caveat that these are very small devices, so we've not yet made large area devices. Well, if this is really due to zero-point energy, that would mean that as we widen the Casimir cavity and exclude fewer modes, we ought to be getting a lower current. And that's exactly what we see. So this is the short circuit current as a function of the cavity thickness. And the thicker the cavity is, either for the organic PMMA or for the glass SiO2, we do get a fall off in the current. There are a number of other measurements that we made on these devices, which I'm not going to show right now for lack of time, and we have discussed them previously. But I will very briefly address the issue of the reliability of the results, because this is, if it is correct, quite important. We verified these results in over 30 batches of devices and measured thousands and thousands of devices. There is scattering in results, but we consistently see these trends. So could this be due to some sort of a measurement artifact? We spent a long time looking for measurement artifacts, and I'm going to very quickly go through 9 tests we made for measurement artifacts. One question is whether this degrades over time. Is it some sort of chemical effect? And the answer is no. The current is continuous over time. This shows 4 hours. We've actually upped this to 24 hours. If this really is due to this sort of photoelectric effect that I'm talking about, it ought to scale with area. And in fact, it does. We've made devices between these submicron devices up to devices that are 100 microns on the side, and it scales with area. Well, does it scale with number of devices? So we've made 2 types of small arrays. These are 4x4 arrays. And we find in these arrays that when we have a 4x4, we do get 4 times the current and 4 times the voltage. Might it just be due to something in our processing, because we're cooking the devices as we build them? So we made measurements first with the basic metal insulator metal device. There was no current. We heated it to the temperatures that we would use for processing, no current. We added the dielectric, the transparent layer that we have, and for making the Casimir current cavity, again no current. Only when we put the mirror on do we all of a sudden see a current. Okay, well, might it be due to some sort of a leakage effect? You've got this thick Casimir cavity on top of a thinner metal insulator metal. Might there be some charge building up there that gets through? So we measured the relative resistance of the Casimir cavity and the metal insulator metal device. Casimir cavity is at least 1,000,000 times more resistant. It's very unlikely that any charge that's built up there could get through and give a significant current? Might it be due to electromagnetic pickup from the ambient surroundings? We did our measurements in a mu metal box and an aluminum metal box, and then we checked for low frequency and high frequency electromagnetic pickup and found neither. Might it be due to some sort of a thermoelectric effect? There could be two. One is thermoelectric effects within the device itself due to very, very slight temperature differences, or thermoelectric effects between the device and the measurement apparatus. So we did some thorough testing for both of those, found nothing, no effect. And then just recently, we carried out another type of test, and this was actually recommended to us by Jeremy Monday, and that is maybe there's some sort of a field effect. Maybe there's a voltage that builds up on the mirror, and that voltage somehow induces current in the metal insulator metal device. And so we did a measurement where we varied the voltage on the mirror up to 10 volts to see if it changed the current through the MIM. The answer is no. All right, so that's for those kind of sanity checks. What about some sort of external source? For example, might it be due to cosmic rays? Well, the highest flux of cosmic rays come from the sun, and there are about 10,000 particles per square meter per second. And given the size of our device, that would mean that one cosmic ray would hit our device every 160 years. We seem to see a current that occurs more often than that, so I don't think it's cosmic rays. Well, what about neutrinos? The neutrino flux is greater. However, the absorption cross-section for neutrinos is extremely small. It's very unlikely that we could capture them because we can't even get them to be captured going all the way through the Earth, never mind in a very thin subelectron device. So it's not due to neutrinos or cosmic rays. Okay, so that's the results. Now I want to get on to some of the new discussion and mulling over that we're that's related to the topics of this conference. And so first I will discuss the issue of vertical particles and fast capture. So one way to think about this is we know about the photoelectric effect. The photoelectric effect says that light incoming to a metal surface energizes the electrons, and those electrons can be emitted. And this was discovered by Hertz in 1887. In 1905, Einstein codified it as the photoelectric effect, mixing it with Planck's idea of a packet, if you like, of electromagnetic radiation, which we now call a photon. And so if we have this photoelectric effect, it's been measured by shining light on a piece of metal, but if we really have these zero-point energy fluctuations all over the place in the vacuum, doesn't that mean that we ought to just be having this huge stream of electrons coming off metal surfaces? But we don't. Why? Well, one way to answer the question is that the incoming radiation from the vacuum is virtual. These are virtual photons. And the virtual photons aren't going to give us real electron ejection. So let's get into this virtual photon bit and talk about it a little bit. So virtual particles are transient quantum fluctuations. Their existence is limited by the uncertainty principle. They're usually interaction particles. They mediate interactions between other particles, and you don't see a naked virtual particle. You just see the results of it. And it's well accepted that vacuum fluctuations produce virtual photons and pairs. Can you take these virtual photons and make them into real photons? The answer is yes, and it's been demonstrated using the dynamical Casimir effect. So the dynamical Casimir effect involves taking this Casimir cavity and very rapidly moving those plates. You've got to do it at relativistic velocities, and the way that it's actually done in practice is by changing the dielectric of the material, so you're effectively moving them back and forth. And this was demonstrated, and you actually can see the existence of real photons produced from these virtual photons. Okay, well, if you can do that, might it be possible to use fast capture to do the same thing? So use fast capture to capture these photons, these virtual particles or photons or whatever we produce from them, and make it real there. And that's really the question that I'm asking. Can fast capture convert virtual quantum vacuum photons into real photons? And we can get a key to understanding this by looking at evanescent modes. Because evanescent waves, which are well known in optics, are in fact virtual photons. It's the same thing. So let's take a look at evanescent waves and see if we can get some understanding from that. We know about total internal reflection. If we have a prism and we've got light coming into it and it encounters an interface at a sharp enough angle, then we can get all of the light to be reflected. None of it is transmitted if we pass this critical angle. And that's true for all of the power, but there is a strange phenomenon in that we have an evanescent wave. We get some leakage of the electromagnetic energy into to the outside, just outside the prism. There's no power that flows, but it is there. If we take another prism and we put it a few microns away, or a few wavelengths, let me say, away from the first prism, no change. We still get total internal reflection. However, we can frustrate that total internal reflection. And the way we can frustrate the total internal reflection is by putting these two prisms close enough together. If we get within a fraction of a wavelength, then this evanescent wave becomes a propagating wave. And we can get the light to go all the way through, and we can get energy transmitted. So by allowing this close spacing of these evanescent wave, the evanescent wave, we've turned virtual into real. We can do the same thing with electrons. So if we have an incident wave of electrons hitting a barrier, in the barrier it'll tunnel through, and that's an evanescent state. The transmitted wave will then be some fraction of the incident wave, and in this way we can capture some of the incident wave in transmission in the other side. And so in this way we're actually creating a propagating charge by capturing these virtual particles, if you like, or these evanescent particles. And my conjecture is that we're doing something similar in our devices. Okay, so we've talked about virtual particles and capture. Now let's expand a little bit to the topic of this conference and talk about the second law of thermodynamics, and once we're at it, talk about the first law and whether capturing zero-point energy would in fact violate something here. The sensible point of view is that forays into free energy inventions and perpetual motion machines using zero-point energy are considered by the broader scientific community to be pseudoscience. This was stated in a U.S. Army intelligence report in 2007, so it must be true. And so that's the general view. Let's see what we think about it. If we want to talk about the second law of thermodynamics, the first question we've got to ask, of course, is which second law of thermodynamics? And we can go through Carnot's principle, Clausius, Kelvin, and so on. They all involve temperature and colder, warmer, things like that. But if we're talking about zero-point energy, we believe that zero-point energy can exist in the absence of temperature. It can exist when you go all the way down to very low temperatures. And therefore, let's use a statement of the second law that does not involve temperature, and that's Planck's statement. So Planck's statement is that every process occurring in nature proceeds in a way in which the sum of the entropies of all bodies taking part in the process is increased. In other words, we don't have any sort of decrease in entropy in any closed system. And so let's take that as our description of the second law that's applicable. So is there entropy associated with zero-point energy modes in a Casimir cavity? I took this from a publication that looked at a Casimir cavity formed by two metal spheres. Now it can be planes or spheres. I'm using this one simply because it was a nice thought. And this shows how the entropy varies as a function of spacing between these two metal spheres. And you can see that, yes, in fact, there is a variation of the entropy in a Casimir cavity as you change the spacing. So what does that mean? Well, if we wanted to change the spacing in the Casimir cavity and get energy out, yeah, we may be having some trouble with the second law. So a lot of the earlier concepts for harvesting zero-point energy involved allowing the two cavity plates to move together, extracting energy from that. There's a famous paper by Forward on this. And that would produce, in fact, a reduction in entropy. There's also another problem, which I won't get into here, and that is that the Casimir force is a conservative force, so you can't get out more than you put in. So mechanical extraction is an issue. However, our device does not modify the Casimir cavity spacing. We have the same device before we extracting current as we do after we're extracting current. The Casimir cavity is a stationary vehicle for making the device work. So therefore, what we really want to look at is the entropy of the quantum vacuum itself, rather than the entropy inside a Casimir cavity. So what is the entropy of the quantum vacuum? Well, the standard answer from quantum mechanics is it's it's a well-defined state. It's the base state for everything, and therefore its entropy is zero. And if its entropy is zero, that means that if we want to convert that energy into work, we're free to do so, because we don't have to exclude, we don't have to throw out any entropy along the way in order to make it work. So at least on a fundamental level, there's no problem in harvesting the zero-point energy from a vacuum. But there's a corollary to the second law of thermodynamics, which really has to do with perpetual motion. So a perpetual motion machine would do work without an external energy source. And in doing that, it either has to violate the first or the second law of thermodynamics, or both of them. And so let's take a look at what we're doing a little bit more closely and ask whether we're building some sort of a perpetual motion machine that violates a fundamental law. So in order to do that, we need to say what we're talking about when we talk about the quantum vacuum and zero-point energy. There are multiple models of it, and I'm going to describe three here very briefly. One is the standard in quantum interpretation from Bohr and so on. And then there's also stochastic electrodynamics, which I love. It's a fascinating classical approach. And then something that I'm calling the thermal law. So let's start with the standard quantum interpretation. So the standard model, the Copenhagen interpretation, is that the zero-point energy is a fixture. It's just a fixture of nature. It's there. You can't deplete it. You can't add to it. It's just there. So if you have a little box, and you could take all the energy out of the zero-point energy out of that little box, you'd still have the same amount of energy in that little box. So if we accept that, that would mean that removing energy would violate conservation of energy, would violate the first law thermodynamics. Okay, let's take a look at stochastic electrodynamics. So stochastic electrodynamics says that the world is really classical with the addition of background electromagnetic fields that make up zero-point energy radiation. So, for example, if we take a look at an atom, according to stochastic electrodynamic model, the atom has orbiting electron. That electron is, in fact, accelerating, and it's radiating Larmor radiation all around, and so it would wind down and fall into the nucleus, except that there's also incoming radiation from the vacuum, and that dynamic equilibrium between the incoming radiation and the outgoing radiation support electronic orbitals. So there's a balance of emission and absorption. So if we take, and there's much, much more about stochastic electrodynamics, which we're not going to talk about now. So if we take this interpretation of our quantum Aperian world, then what does that say about the first and second laws? So it says that any way of extracting energy locally from the zero-point fields would have to be fed by the surrounding electromagnetic fields. And so in that way, we actually would be conserving energy because we're pulling it from somewhere, but we're putting it in as well. And so the first law is observed, and as we said earlier, the zero entropy interpretation of the quantum vacuum says the second law is also being observed. Finally, let's take a look at the thermal law. So again, this is what I'm calling the thermal law. So if we take a look at the formula once again for the energy density of zero-point energy radiation, the energy density includes a temperature-dependent term and a temperature-independent term, this being the zero-point energy. Interestingly, we can express that same thing mathematically as a hyperbolic cotangent. And so we're actually mixing, if you like, the zero-point energy and the thermal terms. This is just an arithmetic. There's nothing fundamental here. But it sure makes me think that these two things, the thermal energy and the zero-point energy, are fundamentally tied at the hip. Are they somehow combined? For example, even though our quantum mechanical viewpoint right now certainly doesn't say this, is it possible that if we were able to extract zero-point energy, we'd have to feed it with thermal energy? And so the location where we extracted it from would cool. So in that way, if zero-point energy and thermal energy come from the same source, extracting zero-point energy would produce cooling. We would obey the first law because we're getting real energy from somewhere, but we would be violating the second law because cooling an ambient situation in equilibrium is a clear violation. So which of these three models do we take, or is there another model entirely? That's up to you. Okay, so let's take a look at the summary of our results so far. We've made Casimir cavities adjoining ultra-fast charge transport devices. They produce power. We've shown that the form for this power varies as we would expect it to if the source of the power were zero-point energy. And I wasn't able to show you all of that. Our papers describe it in more detail. We've looked carefully for artifacts, and at least so far we've not been able to find any sort of artifacts, and our measurement apparatus is the most sensitive available. We're also starting to get some measurements from outside labs that are corroborating what we're seeing, but we haven't yet done that to sufficient accuracy for publication. We've written 2 papers on this so far. So what are the consequences of all of this? If the measured 70 watts per square meter power that we found in our small devices, if that could be reproduced over large areas, and if we could take these and stack these devices, I mean, there's no reason we can't go into the 3rd dimension, we could quite easily get lithium-ion battery power densities. We could make a very practical power source. What's the consequence? It would be revolutionary. Okay, so let's go quickly to the last part, which is the unanswered questions. One question is, why do we not see a large photoelectric effect from zero-point energy at all metal surfaces? And I raised this, and the standard answer is that the photons, or we shouldn't even call them that, the electromagnetic modes from the vacuum are virtual. Can we use fast capture to convert those particles, those virtual particles, to real particles? I don't know. If the zero-point energy hot electron excitation between both electrodes exists, why isn't there a huge conductivity even in the absence of a Casimir cavity? Well, the model of Larry Ford says that in fact we do require a cavity for the electron injection, and he discussed that briefly earlier in this conference. However, Larry is very clear to say that he does not have an asymmetry. In other words, current goes in both directions. So it's not an explanation for the currents that we're seeing. So if there is symmetric excitation, why don't we see currents in both directions? Why do we see an asymmetry? And I raised the conjecture, is that due to fast capture? Or are we really looking at this whole thing the wrong way altogether? And is there another model for operation that fits our results a lot better? It's really early in the game, and it's too soon to tell. Thank you.
Thank you, Garret. That was a wonderful talk. So I'm sure we'll have some questions here. We'll get to the participants. Okay, we'll start with Kent Peacock.
Thanks very much, and fascinating talk. I don't quite understand every detail of it, but it did strike me that there may be an interesting parallel between your work and Schrodinger's observations in 1943. So Schrodinger published a famous book called What is Life, in which he asked himself, how can we account for the thermodynamics of a living organism? Because a living organism, as long as you're still alive, it maintains a roughly constant level of entropy. And how is this possible without violating thermodynamics somehow? And he realized, of course, that it's because we metabolize, and in the process, we're pumping entropy out through infrared radiation from our bodies, from when we exhale carbon dioxide and so forth. We're pumping, so we're actually creating more entropy, and we're, I guess you could say, preventing within our bodies. And so nothing gets violated, but you can create local areas where the entropy is either constant or lowered, but there's always an energy cost. So you have to, so I sort of compare this to, like, imagine there's a giant pile of basketballs on the gym floor, and it's going to fall down very easily, and you've got to always keep on putting basketballs back onto it to hold it up again. So anyway, I just throw that out. Is there any parallel between what Schrodinger was talking about there and what you're talking about?
So, from a conventional thermodynamics point of view, I'd say no, because we know that we can reduce entropy by adding energy to the system, and as in What is Life from Schrodinger. In this case, we're actually extracting energy. And we don't seem to be paying any sort of entropic cost for that. So, you know, I really don't know. I mean, I honestly and totally don't know. But I'm not sure that we need to take that approach.
Okay. I'm willing to bet the energy is coming from somewhere, but
well, I believe it is.
It's certainly not to question your results, but we might be surprised where the energy is coming from, but I'll just leave it at that.
You're probably right.
Well, okay. Paul Minker.
Yeah, I just had a couple, maybe more comments than questions, but it is interesting that, you know, in some sense, all these quantities are formally infinite, the energy of the vacuum. So, if you're using kind of underhanded math, you could have, you know, subtract a finite amount of energy from an infinite vacuum and not kind of change that. But I think what this might be touching on Planck level quantum gravity questions, because, you know, the vacuum energy breaks down at the Planck scale. Otherwise, everything would turn to a black hole. And like all of these ideas, like quantum field theory, formally breaks down. So it's really interesting that this could be an avenue into these, you know, very pressing questions one day. But maybe for more of a question, do you see any like true challenges to scaling up the size aside from like the normal logistic challenges, or is there any like theoretical or engineering reason to think this is like only valid at small scales?
No, I think it can be scaled. The big problem that we're having, and the reason that we're slow doing that, is that we're using metal-insulated metal devices, which are essentially all interface. And I think George in the previous talk talked about how really the devil lives in the interfaces, and it's a challenging technology. So at this point, it's a technological issue.
Sure, because, you know, there's nothing in principle wrong with a small effect. I mean, you know, G minus 2 is in the 10th decimal place of fine structure constant, but there is, on the rhetorical side, something a little more convincing, I think, to a general audience about just a larger effect. You know, there's the unknown unknowns, you know, and the larger the effect, the harder it is to explain. It's just something we're not thinking of, you know?
Yes,
Yeah.
I absolutely agree.
Wonderful talk, thank you.
Thank you.
Justin Coven.
Hi, I'm going to elaborate a little bit